Hello friends, I hope you all are fine. So let's start the today's topic, and in this we are going to cover the proportional controller. Let me tell you the overview of controller. This is the part of industrial controller of control system. In that we have proportional controller, then we have integral controller, then we have a derivative controller, and apart from these we have a PI controller, PD controller, and the combination of all three PI controller. Okay, these are the various controllers which we use in a control system analysis. Okay, so these are the topics which I'm going to cover in separate videos. So the first we will cover this proportional controller, and let's see what's the concept and what are all the analysis involved in the proportional controller. Okay, so uh, first of all, let me tell you, controller is a device used to improve the performance of control system, that is to drive the plant towards desired output. Okay, and if we talk about the proportional controller, in proportional controller the actuating signal, this is the main point over here, the actuating signal of the control action in a control system is proportional to the error signal. Okay, so actuating signal is proportional to the error signal, we can call it as a proportional controller. Therefore the system is called proportional control system. Okay, so actuating signal A of t is proportional to the error signal E of t. So in that case we can say it is the proportional controller. Here itself I have given a block diagram. You can see block diagram. In this block diagram here, the input is the reference signal R of S. Here is the summer, and here is the error signal. Here is the controller transfer function Kp. Here Kp is the uh, proportional controller transfer function, like parameter Kp, and the next is the actuating signal P of S. Here is the transfer function of the plant, like you can assume any transfer function which is related to the plant, and here is the output, and from the output itself there is a feedback given to the input, and this feedback is the negative feedback itself. Okay, so this is the basic block diagram which we are going to use in the entire proportional controller implementation. Okay, yeah. So the next point says proportional controller is a natural extension of on-off controller. As you all know, like this on-off controller is a discontinuous controller. Discontinuous controller, and you can refer any theory book of control systems to read about the on-off controller. But this point is important to remember, like the proportional controller is a natural extension of the on-off controller. Okay, so as you can see over here in this diagram itself, uh, for this particular range, from this range to this range, the A of t is proportional to the E of t for the particular range. So you can say over a particular range, uh, A of t is proportional to E of t. Okay, and this range we can say it is a proportional band. Proportional band, you can say, over the range. So in this proportional band range, A of t is proportional to E of t, where A of t is an actuating signal and E of t is the error signal. So when you remove the proportionality sign, you will be introducing a constant which is known as Kp into E of t. Okay, so this Kp is what we call as a controller transfer function, which is Gc equals to Kp. So this is the important part for the proportional controller. Like what is the controller transfer function? We can say Gc, which is equals to the Kp. Here Kp is the constant. This is the constant. Okay. Okay. With the graph itself, you can say in this proportional band from here to here, A of t is proportional to E of t, and the slope of this line is given by the Kp. So Kp is just the magnitude of the slope of this line over here. Okay, and this particular range is known as the proportional band. Okay, and one more thing, there are few questions asked on this proportional band. So you can say Kp is equals to, you can just highlight it, like Kp equals to 100 divided by proportional band, and generally proportional band is expressed in the percentage. This formula is very important, and many times they have asked in the exams, like if Kp is given, what is the proportional band, or you can write like P proportional band in percentage equals to 100 divided by Kp. So these are the small formulas which you should remember while solving the proportional controller questions. Okay, yeah, here I have written 2 points. So first point says practically proportional controller is an amplifier. How it is an amplifier? In practical case, if you see, uh, when you increase the value of this Kp, So generally it is just the output by input equal to some constant. So when you increase this value of constant, generally your output will be increased in that case. So when you increase this, output will be increased. So in that case, we can say it is an amplifier, like amplification of given input. So you can call it as an amplifier. Okay. The second point says proportional controller has a good speed due to which the control system becomes faster. Since output is proportional to input, therefore we can say it has a good speed. Since there is a no lag between the output and input, that's why it is uh, making our system faster. So you can say the control system becomes faster when we use the proportional controller. So these 2 points are very important points, and you must remember these 2 points. Actually, these notes are very precise, and with this notes itself, you can solve maximum number of questions, and you can refer to any book in case if you feel this content is less for you. But actually, this content is having all the important and uh, crucial information about the proportional controller, like the analysis point of view. Okay, yeah. So let's come on to the analysis. Like as I have told you, this block diagram itself in the beginning, like here R of S is the reference signal, here we have here our error signal, here is the actuating signal, and this is the controller transfer function block, this is the plant transfer function. I have considered the standard second order system, and with the unity feedback, and this feedback given over here is a negative feedback, like you can see over here. And yeah, with this this block diagram itself, we are going to analyze the controller action, like what are all the parameters which are affected by the controller transfer function. Okay. Yeah, so first point I would like to discuss is without the controller. Okay, so without controller we have a characteristic equation Q of S, which is equals to you can say S square plus 2 zeta omega n S plus omega n square, which is equals to 0. This is the standard second order transfer function characteristic equation with a negative unity negative feedback. Like as you all know, like when you g of s upon 1 plus g of s into h of s, we have the transfer function in case of negative feedback system. So h of s is 1 and g of s is what this value. So g of s upon 1 plus g of s into h of s, when you substitute this value and when you find the characteristic equation q of s, you will find this, you will get this characteristic equation. Okay, so here I can say the natural frequency of oscillation is equals to omega n, and let's consider it over here from this characteristic equation, this 2 zeta omega n equals to some value x. This implies that zeta, which is equals to the damping ratio, which is equals to x by 2 omega n over here. Okay, and in case of as you can see, this is the type 1 system, like this is the type 1 system. So in case of type 1 system, when R of S equals to ramp input, this implies that R of S equals to 1 by S square. Okay, so in that case we have a steady state error equals to 1 by kV, and here kV equals to limit s tending to 0 s into OLTF. This is open loop transfer function, so you can say limit s tending to 0 s into open loop transfer function is over here, which is equals to omega n square divided by s plus 2 zeta omega n. So this is equals to 2 zeta omega n only. Okay, yeah, so when you solve this limit, you will get this cancel, and kV value will be equals to, when you put the limit, it will be what? So it will be omega n upon 2 zeta. It will be omega n divided by 2 zeta. So steady state error will be, so this implies a steady state error equals to what? 2 zeta divided by omega n. Okay, like with these parameters only we are going to compare, which are in the cloudy structure. I have kept all the natural frequency, damping ratio. This is nothing but damping ratio, and this is the steady state error. You must know like in which case we have calculated the steady state error, which is in the case of type 1 system. Okay, since it is the type 1 system, we have considered the ramp input, and for the ramp input we have steady state error is 1 upon kV, and here kV is equal to limit s tending to 0 s into OLTF. Here OLTF is the open loop transfer function. Okay, So and when you use the controller, like when first we are not considering this controller, in that case we have analyzed this particular without controller case, and now we are considering this controller block, and let's see how the natural frequency damping ratio steady state error are getting changed. Okay, so let's start with controller action. So when you consider the controller action, your characteristic equation will change. So you have two blocks in cascading, so kp will be multiplied with this omega n square. So here the overall transfer function will be like over here, this kp, this entire block will be multiplied with the this multiplication of the two blocks will happen. So in the resultant characteristic equation will be q of s, which is equals to 1 plus g of s into h of s, which is equals to 1 plus, we have kp, sorry, so the resultant, this characteristic equation will be as a square plus 2 zeta omega n s plus kp omega n square equals to 0. Like how you are getting this characteristic equation, let me clarify you. So you will get when you solve this transfer function, you will get transfer function as in kp into omega n square divided by s plus 2 zeta omega n divided by 1 plus but you'll get 1 plus g of s into, you'll get kp omega n square divided by s plus 2 zeta omega n. Okay, so the transfer function will become kp omega n square divided by, we'll get s plus 2 zeta omega n plus kp omega n square, like this. So here is the characteristic equation from this part, 1 plus g of s into h of s. This is equals to the q of s over here. So like this you are getting this q of s over here. You can see these two equations are same. So like this you can get the characteristic equation. Okay, so just I have showed over here. Okay, yeah. Okay, so with this particular characteristic equation, when you see the natural frequency of oscillation, it got changed. So the natural frequency will become root kp into omega n. Like this particular term is the natural frequency square, so root kp into omega n is the natural frequency. As you can see, the frequency has increased. Okay, so natural frequency got increased. So this is one point in comparison to the previous one. Previously it was just omega n, now it is root kp times omega n, so it got increased. Okay, so when there is an increase in the natural frequency of oscillation, like more number of oscillations are introduced into the system, so here more oscillations, which makes the system less stable. So when there is more number of oscillations, there will be a system which is less stable. Okay, here also let's consider 2 zeta omega n equals to some x. Okay, so zeta will become x divided by 2 omega n, and here the natural frequency of oscillation omega n is equals to x divided by 2 root kp into omega n. So the damping ratio got decreased. Okay, so we have less damping which is observed over here. So yeah, in compared to the previous one, we got less damping. So this is damping ratio. Okay, and the third point itself saying for the same r of s equals to 1 by s square, which is the ramp input. Okay, so for this E steady state, like steady state error is 1 upon kV. So that steady state error is equals to, when you calculate the steady state error, so in that case kV is nothing but limit s tending to 0 OLTF, and we have open loop transfer function limit s tending to 0. The open loop transfer function you can see from the block diagram itself. It's just the multiplication of the kp and the plant transfer function. So sorry, here the S into oil TF. So S into open loop transfer function is Kp into omega n square divided by S plus 2 zeta omega n. Okay, so when you solve this limit, you will get over here. So Kv value is Kp omega n divided by 2 zeta. Okay, so steady state error is nothing but 2 zeta divided by Kp into omega n. So when you have Kp in the denominator, so in general, the steady state error will reduce. There is the reduction in steady state error. So it is good for us. It's like you can just classify it like this is the good work done by the control system, proportional controller, and we have less damping ratio means um, like this point you consider for the more oscillation there is a less stable, so this is not good point for us. Okay, so in case of damping ratio it got decreased, so more is the damping ratio, more is there will be a damping, so it is like the parameter which is not desired, so we need a damping ratio more, so there will be more damping and we get the stable output in less number of time. Okay, so it got reduced, so we want it more, so it is also undesired result. Like we don't want it, but yeah, as you can see we have a reduction in the steady state error, which is very good for us. Okay, so this is the entire analysis of the control system with proportional controller, and here are the few statements which I want to share with you, and these are very important statements. So the first statement says, using proportional controller either we can improve the stability of the system or accuracy of the system, but not both, hence the proportional controller alone is not used. As I have told you, as we get more number of oscillation, the stability of the system is compromised, and in case of accuracy we have a less steady state error, so but that is not equals to 0. So in that case we cannot get these two parameters simultaneously. Like when we improve this, this will be compromised, and when we improve this, this will be compromised. So simultaneously we cannot uh, so simultaneously we can't improve these parameters. Okay, so one by one we can do, but when we improve the accuracy, our stability will be compromised, and when we improve the stability, our accuracy will be compromised. For this reason it is not used alone. It must be used with some other kind of controller, maybe integral or derivative, or maybe altogether PID controller. Okay, the second point says, using proportional controller the steady state error can be decreased, but it cannot be 0, and the residual error is called the offset error. As we have observed, like we can reduce the steady state error by means of the proportional controller, but we cannot make it to 0. For the 0 steady state error we need a Kp to be infinite, which is not practically possible to design such controller with the infinite proportional constant. Okay, so in that case we can say like the offset error is always present, and we can minimize the error or offset by using the proportional controller. Okay, so these 2 points are very important, and generally in exam we expect the question which are related to the points. It's like whether the proportional controller having good speed or not, whether it can improve stability and accuracy both at the same time, or whether the steady state can be made, error can be reduced to 0, or we cannot reduce it to 0, we can just minimize it. Okay, so these 2 points are very important, and the final point I want to discuss with you is the implementation of the proportional controller. Like as we all know, in the first step itself I made clear like proportional controller is nothing but an amplifier. You can see over here the structure of the amplifier. Here it is an op-amp structure. So yeah, the output by input, like we note by Vi equals to minus R2 by R1, which is equals to minus some constant Kp. Like here Kp is given by R2 divided by R1. Like you can directly implement by means of circuit itself, like the circuit will work as a proportional controller in case when you use this particular circuit in cascading with another circuit. Okay, so this is general implementation of the proportional controller. As you all know, like the virtual ground concept you can apply over here for the op-amp. Virtual ground concept, like the potential over this point is equals to the potential over this point, so you can say here is also 0. So when you assume the current like this, so 0 minus Vn divided by R1 equals to 0 minus V0 divided by like V0 minus 0 divided by, sorry, we can make it like this. Over here you can assume the direction of the current, like from here the current is going like this, and from here the current is going, so here the current is going as 0 amps, and here is the potential 0. So Vn minus 0 divided by R1, which is equals to 0 minus V naught divided by R2. So from here, V in by R1 equals to minus V naught by R2. This implies that V naught by Vi equals to minus R2 divided by R1. Here you can use R2 by R1 as a parameter Kp. Like here it is coming as a minus Kp, but you can just invert the output and you can get it as a Kp, positive value. So with this circuit itself, you can implement the P controller. Okay, so it's a very easy topic and you can easily do that. Okay, yeah. So this is all about the proportional controller, and yeah, thank you very much.